Okay, so today, what I'll do is just finish a formula about not complex, polar coordinates on how to do areas in polar. And then we'll move to discussing complex numbers, which is like a very fun topic. We'll just do like the very minimum because, it's really like a big topic, but I'll kind of give you like the cliff notes of like how they work. Um, And yeah, and those for those who came in late, I will have your exams created by tomorrow. Okay, so let's talk first about like area, like in Calc 1, like when you had like a function of one variable, right? What was like the area under the curve? So let's you know go back to Calc 1 for a second. Just to make the diagram easy, let's say you have a function y equals f of x, um, and then you had this interval a to b. And then, as you well know pretty well, like this area, like the area of this region, was just like the value for the definite integral from a to b of the function, right? Now, this is somewhat implicit and it's not stated in those terms because maybe it's a little bit too obvious. But when you say like the area, under the curve or something like that, it's not really only the function itself that you're thinking about. Like this region, if you thought about this region on the plane, it has kind of like four walls. One wall is like this vertical segment. The second wall is this other vertical segment. Then this interval AB on the line, and then the kind of like the only one which is kind of interesting, which is like the curved one, is like the function. So this region is actually being determined by four things: two vertical segments, a horizontal segment, and the curve, right? It's just like the other three things, they're so simple, like you don't really mention them explicitly, but it's actually good to keep that in mind. So if you call this region R, R is determined by four things, by the vertical segments. And I'll use different colors so that it's kind of more clear, like X equals A, uh, X equals B, the horizontal segment from A to B, the horizontal segment, A less or equal to B, right? So that's this piece. And the more interesting one, which is like the actual graph of the function, right? And the graph of the function. The thing is, like, like the vertical segments are kind of like implicit the moment you write the bounds, it's kind of clear which ones you're referring to. But it's kind of better to think of if you think about this as a room in two dimensions, it's like it has four walls and really like two are vertical, one is horizontal, and this other curving one. Yes. Uh, X is between A and B, yes. Right, like which is the interval, right? Oops. I don't know if I wrote that correctly. Right, like these points are where X are between A and B. No, 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 yeah, yeah. So, but And you'll see why this comment is useful in a moment when I tell you about how we're going to do like the integral in polar. Um, So last time, what I want you to remember from what we were saying last time is that in polar coordinates, typically when you have like the equation of a curve in polar, you solve for r. Like that's kind of like the most easy way to do things. So in polar, when you have the equation of a curve, you have the equation of the curve, an equation of representing a curve. Um, you usually solve for r. So just to give you like some examples of what I mean, which some of them we worked out last time, but kind of like the most obvious one is like, well, what if you had like an actual circle, like, x squared plus y squared equals 4? If you go back to polar, if you rewrite this equation in polar, you get r equals 2, right? Um, Another example would be like, I mean, just to kind of like stick to circles, so it doesn't have to be a circle. Uh, You had like a circle, like kind of like center here, uh, you know, 0, 1, then like, which was x squared plus y minus 1 squared equals 1. Let's say it's a unit circle. Then if you write that in polar, then you'll get that r equals 2 sine of theta. Here's let me give you another example, which is not a circle, just to show you that obviously you can have more interesting things. So there's like a curve called the cardioid, which is really cute. Like, let me see if I can show you the animation on GeoGebra, and then I'll write like a formula for it. I'll tell you, once we talk about complex numbers, I can actually give you like a trick to find the equation of the cardioid, which is pretty elegant, but let me just see if I can show you this first on GeoGebra. Huh. Yeah, I like this one a lot. So the way the cardio is produced, again, you don't need to kind of like, the construction is just to illustrate where it would come from. Like I would just write the formula and then like that's good enough. But kind of like, imagine you have like a fixed circle. Like you have a circle on the plane, and then you have a second circle, and this kind of like starts rolling about the first one, like the fixed one. And then on the cardioid, what you'll do is keep track of one of the points on this circle's second circle. So you'll see what happens here. So just imagine like this, like the black circle starts rotating, and notice that you're keeping track of the red dot. And then you get the cardioid. Okay, so that's like a very famous curve. So like the curve itself is like the red curve. Again, there's like a very elegant way to find them using complex numbers, which I'll tell you about later. But here's another curve that you could find, for example, and I'll kind of like write for it like the equation in polar, but I just wanted you to like kind of see it first. Like, there are different ways to arrange this, because like you could have like the first circle center somewhere else. So for example, if you go to Wikipedia and just like enter cardioid, you'll see kind of like all the different ways in which it's like can be described. Oh, there's like a cute animation there as well. And then there's like, this is like a different version of the cardioid. They kind of like always like look the same, but there are different ways to generate it. like you can move the circle a little bit to the left, and that way the kind of like this cusp touches like the origin. Anyways, my point, my only point for doing this is like to show you, okay, there are other interesting curves, and this one has like a very cute way of writing it in polar. So if you have like something like the cardioid, let's see, yeah, I'll use this one like so, which is has this shape. I'll choose like this version of it. Finding the equation in terms of x and y is actually kind of messy. But like in terms of polar, the equation is just r equals 1 minus cosine of theta, which is really simple. So again, like there are certain extra assumptions that you have to make, because like it could have different radii or different things. But this is kind of like one way to think about it. Yes. Oh yeah, yeah. Here. My only point for illustrating all these different possibilities is that you see that in polar, typically when you have a curve, you give r in terms of theta. That's how you should think about most of the equations in polar coordinates. That's like a good rule of thumb. Uh, like, of course, if you could solve, for example, here for theta, right? There's nothing against that, but then you have to take our cosine, and why would you want to do that to yourself, right? Like, it's kind of messy. Or here you could also solve for theta, right? But then you have to do r over 2 equals sine, so theta equals arc sine of r over 2, which is a mess. Like, so usually the thing is like, since theta tends to appear typically in either in as a tangent or cosine, so solving for theta is like a bit messy. So usually it's just easier to leave the equation for r. Okay, so where am I headed for here? The thing is that imagine, like, for example, I wanted to find the area of this circle or the area of this circle or the area of this cardioid, right? Kind of like this, like the amount that's inside the cardioid. Okay. So the idea is that in these cases, it is actually to kind of like try to think about the area in terms of polar coordinates and instead of like x and y. Okay. So kind of like the setup that we'll have in mind is that you have like a curve. And let me just draw the curve like this. But think of the curve as being given in polar. So like r is being given as a function of theta. Okay. So as I was saying before in Calc 1, right? When you were finding areas, what did you have? You had the curve, then you had these two vertical lines, and then you had the horizontal line or segments, right? You actually had four things, right? The curve, two segments, two vertical segments, and a horizontal segment. So kind of like by analogy, if you want to find the area in this case, what I'll use is kind of like the curve, but instead of like horizontal or vertical lines, because it don't work as well in polar, I will use rays. So I'll kind of like draw two rays. And so I kind of will find the area. And if you see here, I just need three things. You need the curve and the two rays, and I'll find kind of like the area that's equals by these three things. Yeah.
So it's just like a more general question about polar coordinates. Like, if you have R, which is like a unit of line, how can you write it in terms of theta, which is in like units?
Oh, yeah, yeah, of course. Sorry about that. Like, kind of like I put that under the rug. Like, so usually if you actually wanted to do this, you multiply this kind of like R0, where R0 is kind of like the radius of like the original circle that you do the rotation like about. So like it's really, it's kind of like the same when you write like y equals x squared. It's kind of like the same objection that you could raise there, like, because how can you equate y with x squared because they have different units? So like secretly there's some magical constants you're multiplying everything by so that the units cancel, right? So here, like, if I had one, and this is actually how it's written in Wikipedia, just to go for like a second. If you go to Wikipedia, I mean, like, again, like there are different ways of writing it. But it is written this way where like A is kind of like the radius of the circle, and then the units are fixed, you see, because, but yeah, of course, like that is like a fair objection. But in most of the math equations, you kind of like forget about the units, so like that's what I was trying to do there. But if you actually wanted to keep track of everything, you could, and then like this expression just gets multiplied by the diameter of the circle that you're using to roll about. Yeah, but so yeah, usually whenever I write an equation, only when I want to kind of like derive it, then I do worry about the units to make sure that we didn't do anything crazy. But usually if it's just like, oh, this came from heaven, like, just write it down. But yeah, like in practice, it is good to kind of keep an eye for that. But yeah, we're kind of like pretending that all that got fixed here when you write down the equation. Yeah.
Axes are labeled by X, but the curve is defined in terms of R and
Mhm. Well, it's kind of like the same, it is the same idea here. Like, for example, like the circle itself, right? Like, like the equation of a circle, you can give it in terms of, uh, this is the thing, that's why I think I mentioned this in class, like it is better to think about this as kind of like a translation. You have two different languages. You have the Cartesian language, like the Cartesian people use X and Y to communicate. The polar people use R and theta to communicate. There's this thing called the circle. The circle, it is kind of like something out there in the world, right? And then the Cartesian people refer to it using this word, right? The polar people refer to the circle using this other word, but it is a word for the same circle. So for like literally, if you look at this, like, it is almost like a linguistic substitution of like, instead of writing x squared plus y squared equals 4, I can just switch to polar and it does become r equals 2. Um, but they are kind of like two names for the same object in space, you know what I mean? Of course, you could have drawn this in the r theta plane, which we did a little bit like last time. Because kind of like this is kind of like the preferred way of drawing things for the Cartesian people. So you could draw things according to how the polar people would draw them in their, like, hieroglyphics or whatever. But it is kind of like a besides the point, because it is kind of like the circle is out there in the wild, and you're just like naming it. It's kind of like you're taxonomizing the circles. So here you are a conduit, right? Which is kind of like this heart shape almost, right? It's actually like a heart if you turn like upside down, right? So like the Cartesian people like refer by it by a crazy equation. Like this is like a crazy equation in terms of x and y. You don't want to try to write that. But the polar people have like a very easy way to describe it, which is r equals 1 minus cosine of theta. But so it doesn't, right? Of course, if you drew like this on the r theta plane, it looks more like the curve of a cosine, right? So it won't look like in the same shape, but it is kind of like just kind of like how do you label it in terms of the new language, if you know what I mean. So in that sense, it's fine to have like the same curve with two different variables, even though they're being drawn in terms of like the x-axis and the y-axis. By this I just mean how this is an equation in terms of x and y, which I don't want to write because it's very complicated. But if you translate it to r theta, this is how this would look like. I mean, if someone has taken German, like German has so many long words, like I'm sure like, and like there's so many languages where like you have like these long expressions for a word and then you translate it to a different language and it simplifies. Actually, English is very useful for those things, like, because there are many things that just become way shorter than other ones. But, and so it's kind of like the same principle, right? But the curve, yes, it's being drawn on the XY plane, but that's fine, just because that's our preferred way of drawing them, because that's what you would actually see with your eyes. You know what I mean?
So the R and theta graph is gonna look different.
Oh, totally. Yeah, it would look more like the graph of a cosine, right? Like it would, yeah, it's kind of like it looks like the graph of cosine, like well, minus cosine, right? Like shifted by 1. Like actually, this is what maybe it's easier to draw the other one because in the r theta world, right? Then r equals 2 look like a horizontal line. That's right, what I had said, right? Um, But it's kind of like if I said r equals 2 and I wrote next to this like x squared plus y squared equals 4, like that's totally fair. Like, you just have to understand that, the pictures do look different in their respective languages. Correct. Yeah. I mean, no, like it is like a fun game of like having like the perspective, like the right perspective. It's just like it is weird to do this, but of course, like I could also write the name in the r theta world for the circle and just write x squared plus y squared equals 4. It's just like this is kind of like our preferred drawing because it's kind of like what we see in a sense. Does that make sense? But the point is kind of like the philosophy behind this is that to show that there's sometimes an asymmetry in the sense that sometimes it is way harder to write an equation in one of the languages compared to the other. So like, again, I don't want to even try to solve, like write this, I mean, I could, but I don't want to try to write this in terms of x and y, because it's kind of like messy, like, but this is relatively simple in terms of r and theta. Okay, so what I was trying to say is that, and when you do, if you have a curve, if you have a curve and you're choosing to write it in terms of polar, but the curve is still being drawn on the plane, on the xy plane. But if you choose to write the equation of the curve in terms of polar, when you find the area, kind of like drawing these vertical lines don't work that well in polar because the equations of lines in polar are kind of messy. I think the workshop will have one of those where you can try it. You'll see it's not that neat. But in polar, it is a lot easier to draw these rays because they're just like at a fixed angle. So the area, when you talk about an area in polar, basically what you think about is that you have a curve and you have two rays and you are trying to find the area of this region. So we're trying to find the area of this region. Determined by the curve and two rays. R equals f of theta and two rays. At angles theta 1 and theta 2. Is that okay, everyone with me so far so good? Is that making sense?
So if this is an X and Y, why don't we still do?
I mean, it's just you could it's just like, again, the thing, if you try to do it directly from the R theta perspective, is that there's this distortion that appears, right? That I had mentioned before, last time. Like, so for example, what I had said, like, last time is that if you kind of like draw this curve on the R theta plane, right, this becomes a horizontal line. And then the form, like you would say, oh, okay, then this was a disc, and then it becomes like a rectangle here. But the area of the disc, it would not be like the area of that rectangle, right? Like there's this distortion. And it is actually so understanding the distortion is what you do in Calc 3. So if you take Calc 3, there's this Jacobian thing and a bunch of other stuff, fun stuff that happens, which explains how to find that. But I'm kind of trying to, since I don't know how to compute the area in the other world yet, and we won't learn it in this class, like, I'll just kind of try to find the area from the real world, because in the real world, I do have like an accurate way of finding the area. You know what I mean? Does that make sense?
Yeah.
But right, like what I'm saying is like the areas, you could try to find the area in this world direct, like, you could try to find the area in this world, but you have to kind of take into account the fact that the shape was distorted, right? And understanding how the shape is distorted is a little bit of a detour into what we want. So that's why I won't do it that way. But you can, yeah. And then that way the picture could always be drawn in the R theta world, and then you can forget about the real world, like you stay in virtual reality and then you find the areas there always. Is that okay? Does that make sense? Yeah.
Still finding a function if we're it's basically saying that each point on the curve can be
Yes,
An R that starts with the origin.
yes, yes, correct. Okay, so now just to show you how you would find the area, kind of like it's the same philosophy as you would find the area in Calc 1. So what would you have done in Calc 1 to find the area? You approximate by rectangles because rectangles kind of like work nicely, with this shape because you have these vertical walls. That's why rectangles kind of work well because then you can just stack them together, and you don't have to worry about that. But in the case of like polar, like if you try to do rectangles, I mean, that is a mess, like because like kind of like they're changing both like the base and like some like rectangles will not work that well because sometimes like 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 they kind of get it looks more like sometimes you would like to use like a triangle or like how the breaking happens is like a little bit less clear. So instead of like doing rectangles, you approximate the area using like circular sectors. So let me see if I can show I have it there. Or like the pizza slice method, which is like another way of calling it. So you have the curve here, you have these two rays, right? Imagine like this is like a part of a pizza pie, and then you cut it with the knife in the rays, and then that gives you kind of like some circular sectors here. There can be kind of like some leftover, you know, there can be some leftover region in the same way in which when you approximate the area by rectangles, sometimes it doesn't cover everything. But if you kind of like chop it thinner and thinner and thinner and thinner, like imagine us being able to shrink these circular sectors, like into thinner bits and slices, like this like white space like will become smaller and smaller. Okay. So the idea here is that and that's why I chose two angles because then the cuts can be made more easily, because they're radial. So it's kind of like you put like your knife, you think of it a pie of pizza, you put your knife and cut like it radially. Okay. So you want to approximate the area using these sectors. I guess that's kind of like the idea. And I'll give you what the formula is. So the idea is to approximate the area. And again, there's like, if you take out 3, you'll spend way more time doing all these things. Like, this is kind of like a preview of what you do there. Approximate area using circular sectors. So what I mean by that, just to kind of draw the picture again, is that you had the curve. And let me try to do something a little bit more curvy. I draw a bunch of rays. Again, this is like kind of like the initial ray. I'll put in purple the initial rays and the final rays. So I'm making my cuts in between those. And then I have these sectors that you see here. Well, actually, let me just focus on one of these. Let me focus on this one because it's a bit nicer. So the idea is that for this sector, the cuts, right? Like there's like a small angle that you use here to make the cut of the slices. So because it's small and this is calculus, you call the angle d theta because it's like a very small angle theta. So there's this angle d theta here. So actually, let me see if I can draw this picture separately just to make it more clearly the focus of our attention. So like, what is happening here is that you have this, let me exaggerate this a little bit. So that it looks more closely like a pizza slice, right? So this angle is called d theta because it's really, really small. And then the radius like of this arc is just r, like how big is this sorry, ray? How big is this ray? Like, I mean, I don't know, I'll call it r. Right, but if this ray was made at an angle theta, if this ray was made at an angle theta, if there's like an like angle theta with respect to the x-axis here where you made the first cut, then this because like the curve is r equals f of theta, then the radius of the value for r would be f of theta. Okay, well, sorry about that. And then the idea is like how much, how big is this area? And there's like a formula in class geometry for the area of a circular sector is just 1/2 the radius squared times the angle, like so. So this has area, this piece has area equal to 1/2 times the radius squared times the angle. But the angle is theta, so you get 1/2 times the radius squared times the theta. And what is r squared? That's the function squared because again we're giving r in terms of theta. And then the total area would be the sum of all these mini areas of all these pizza slices, and then you do that by integrating. So the area, the formula for the area would be the integral from the initial ray to the final ray of 1/2 of f of theta squared d theta. Oh, the thing is like kind of like that is like the formula for right, like there's a tendency what to explain. So if you have a disk, right? Let's call this angle alpha so that it doesn't get messed confused with the other one, right? And you have like a circle of radius r, right? How much should this area be? Well, this area should be pi r squared, that's the area of the disk, times the fraction of the angle, like what proportion of alpha, like, kind of like the ratio of alpha divided by 2 pi, because that tells you how much of like the entire circle you're picking up by the angle, if that makes sense. Then the pi's cancel, then you get the 1/2. So it's kind of like that, which makes sense. If you take a quarter of a disk, what should the area be like? Like, like a quarter of the area of the disk. It's just like the proportion of the disk that you have graph is measured by the proportion between the total angle, sorry, the angle that you make the cut off compared relative to the total angle. And that's where it comes from. Like, I'll draw that. Sorry.
So like, are you saying that these two sectors will have the same R and then and there would be like no like small space there?
I'm saying that in the limit, right? If you were to make this thinner and thinner and thinner and thinner and thinner, then this kind of like like the missing out, the region that's missed out kind of like goes to zero in the same way, which for why when you approximate the area by rectangles in the limit, that kind of like, because the thing is like in the limit, imagine like shrinking this almost becomes like just like a thin ray, right? Like it has no, it's kind of like saying, like this is like the usual conundrum of calculus, because when you have like the area originally, right? And the thing is like, people like to say that the area is kind of like this, right? Like the thing is that you cannot say that literally because like lines have no width, so they have zero area. So that's why you have to thicken them up a little bit so that you have like an area of a rectangle that you can approximate. And it's kind of like the same as in here. What I would like to say is that this area is kind of like, we build up out of these rays, but these rays have no area because they have zero width. So I have to thicken them up a little bit, right? To find the area, but then you do want to shrink them back by taking a limit. So there's like a limit involved as usual. But yeah, like the things like GeoGebra didn't have like good animations for this, so that's why I didn't show one of those. But like you have to imagine just constructing this piece of slice that's thinner and thinner, and then you see like the region being covered more or less identical to the red area that you were interested in. That makes sense. Is that making sense? But yeah, just to write this formula for the circular sector, like if someone wants to have it somewhere in here, what I was saying is that the area here is pi r squared times alpha over 2 pi. And that's what I was using there. So again, the idea, so the difference is that just to compare this with so this is like the area in polar. And then the area versus, right, if you wanted to compare this versus like the area in Cartesian, where like it's an integral from x1 to x2 of f of x dx. So what I was saying last time is that this formula, like that's why it's always useful to think about it in terms of units, because in terms of dimensional analysis, this is why units has units of length. So length times length is length squared, which is area. And this is representing r. F of theta is representing r, right? So this becomes r squared, right? So r squared has units of area. And d theta has no units because it's like radians. So radians, they're not really units, they're kind of like dimensionless. So this, like, even if you don't, even if the entire derivation doesn't make a lot of sense, at least this kind of like explains why you cannot just, why you do need to square it so that the areas come out, like the units come out to be correct ones. Okay, so let's do a quick example about finding the area, and then I'll kind of like start like a brief intro to complex numbers, which will be the main focus of like the remaining two classes, like on Wednesday and Monday. But at least I can give you like an introduction to them today. And I did send you like a video if you want to watch it, which is really fun, like about the history of the complex numbers, because the way I'll explain them is using a little bit of vectors, which makes it a lot easier to understand, but does not. So sometimes complex numbers are called imaginary numbers. And so like the word kind of, again, I think I mentioned this before in class one day, like the word reflects the bias of the time. So if you call a number imaginary, it's kind of like, oh, it's in your imagination. So people didn't take them too seriously. Then there are the real numbers, which are like the usual numbers that you know from the number line, right? And then again, if you say something is real, like that's kind of like, okay, that is actually true. And then and then they're more like classifications, right? Like rational numbers, irrational numbers, and things like that. So let's just find the area of the cup of the cardioid, just to show you how that works. So like as an example, find the area of the top half of the cardioid. And again, just like to show you the picture, the cardioid was this one. And so I'm looking at the top half, so like the half that's above the x-axis. Or something like that. I will give you the pictures in this product. I would put it. Yes. Exactly. Oh, right. Like that's actually what we were going to like. I was about to discuss, but in this case, like, you have to imagine, like, okay, let's actually think about this for a moment, right? Imagine if someone said, okay, what if like the bounce were it started at 45 degrees? Well, that cannot be the case, right? Because 45 degrees is here, right? So if you started at 45, you would be missing all that other stuff below the red line, right? So it cannot be 45. Maybe someone says, well, what about 30, right? But if you put 30, then you're still missing stuff, right? So if you zoom in, if you continue zooming in, you see you can kind of like keep dropping the angle until you hit 0 degrees because the way the cardioid meets the x-axis completely like like the x-axis is kind of like tangent to the cardioid at that point. So like the angle has to start at 0, and then like you make the cuts, they increase, they increase, they increase, they increase. They're here, you're around 170. You keep increasing the angle until you get 180, and then you kind of like have like that top half. Is that making sense? So like the angle would be from 0 to 180. Yes.
Oh, are we doing this in terms of degrees or?
Oh, and for practical purposes, yeah, in radians, so 0 to pi, but I mean, usually I always think it first in terms of degrees and then just like convert to radians at that time of the logging. Um, so yes, like, so in this case, the theta would go from 0 to pi. And so that's all the end of f of theta, right? F of theta would be 1 minus cosine of theta. And so the integral would just be the integral from 0 to pi. So the integral for the area would be the integral from 0 to pi of 1/2 of the function squared, right? That's what you need to remember. And okay, this is not too bad to integrate. We should be able to do it quickly. So this is, how do you integrate this? You can do the squares first. Like, so this is 1 squared, which is 1 minus 2 cosine of theta plus cosine square of theta d theta. Okay. So it's 1 minus 2 cosine of theta. And at least you should remember like the formula for cosine square and sine square in terms of like cosine of 2 theta. So cosine square of theta is 1 plus cosine of 2 theta over 2. So I'll put that here. And once you have it like that, like then every term is like not about to integrate. So you would get theta minus 2 sine of theta plus theta over 2, right? Plus sine of 2 theta over 4, right? at theta equals 0 and theta equals pi. Let's see, yes, that does look well. So, and then you just evaluate, which is not too bad. So theta and pi and 0 gives you pi. Sine of pi and sine of 0 are 0, so like you don't see the sign. And then the other one becomes pi over 2. And you also don't see sine of 2 pi and sine of 0. They also become 0. So I'll just put like, let me just put like minus 0, just to indicate that the signs don't contribute here. Okay, so that gives you what? 3 pi over 4.
No, maybe I was gonna ask, so 6 feet to the area for. Just.
If I had, right, in this case, because the cardioid was symmetric, then yeah, if you just multiply by 2, that would give you like the full area. Which would also have worked if you see it here, if you just had put like 0 to 2 pi, that also would have, like in this case, like you'll see, like it doesn't make like a big difference. Like, you just change the bound to 2 pi and that covers the entire cardioid. What would you going to ask me?
Make it alpha over 360,
I mean,
and then like use that.
yes, that is fine for this formula of the sector. The only thing is that when you find antiderivatives, the antiderivatives of sine and cosine are implicitly done in radians. Because the derivative of sine is cosine only in radians. In degrees, there are extra factors of 360 over pi or pi over 360 because like the conversion. Yeah. Like other, because the thing is like only like if you go back of why the formula works, the way it works, the idea is like in radians, it is only in radians that if you have like a circle radius r and angle theta, that this arc length is r theta. In degrees, it could be times 360 over pi or pi over 360 because like or 180 pi over 180 or 180 over pi because of like the conversion from radians to degrees. So it's only in radians that the derivatives and the antiderivatives are what they are supposed to be. Yeah. But that's the only reason why we do evaluate everything in radians at the end of the day. But psychologically, it's just easier to think in degrees, you know. That's why people find out first degrees. Is that okay? Any other questions making sense? Okay, but yeah, like as I was saying, I would provide the picture, you know, and like the equation for like for the region. So like it's just more like testing out like that you have to square the function, divide by 2. That's like an important part of this formula, just to compare it to how like the area in Calc 1 looks like. Okay, so now just to mention some brief stuff about complex numbers. And again, we'll talk about more about these on Wednesday and Monday. So I'll just mention like something very basic today. So okay, so like maybe like I imagine many of you have had like some experience with complex numbers before, none of which I will assume, right? But if you have heard about complex numbers, then you'll see like, you know, the main character like in the complex numbers, like what makes it new is that you will be allowed to take square roots of negative numbers. That's kind of like the entire like shtick about complex numbers. I mean, this will be called like an imaginary number. I'll tell you more about that. Which from where, if you just took this as face value, right? Like whatever this is, and that's what we were going to try to understand. But if whatever this is, if you just square it, then you get that I square equals -1, right? Of course, like which is not something that is allowed to happen with regular numbers, because when with regular numbers, which are called real numbers, when you square a number, you always get something non-negative, right? So kind of you know, that's what makes these numbers interesting. And again, there's like weird history about how they were found. If someone is interested, you can watch this Veritasium video because it's really good and goes through uh, how they were discovered. But we'll kind of like do like a more like modern approach where we will think about complex numbers in terms of points on the XY plane. And that's kind of like the most geometric way to understand them. Okay, so and so I'll keep this as a black box. I won't refer to this for a moment, and then I'll tell you how this reappears in okay. So a bit later on Wednesday. So we will think of a complex number. As a point x comma y on the xy plane. So I have a point xy, and I'm going to say, okay, no, I'm calling that a number, a complex number. Okay, usually the way you refer to any number, complex number, you call it z. So I'll write this as z. Okay. Instead of p for point, right? Like I could have written equals p for point, but like the way to refer to this are like by using the letter c. Okay, so of course, like you could call whatever you want in the world a number. Like the point like of doing this is that it makes sense to call these things numbers. So what are the requirements for something to be worthy of the name number? So what can you do with numbers? You can add them. For example, you can say 3 plus 5 is 8, or like 3 plus -2 is 1. Okay, so numbers can be added and numbers can be multiplied. And that's kind of like the key thing that makes numbers really interesting. So what can you do with numbers? Can you do with numbers? Well, the two main things is like to add, subtract. These two kind of like come in pairs in a sense. Like addition and subtractions are kind of like two sides of the same coin. And multiply and divide. Like that's the other, like, the other main operation. Okay, so if I'm saying that this should be thought of as a number, what I'm saying is that there should be a way to add points on the plane, and there should be a way to multiply points on the plane. So that's kind of what I'll kind of like explain to you like in the upcoming days. At least the one that's easy to state is like how to add points. So that's really straightforward, and I'll kind of like write that today, and then on Wednesday we'll focus on that multiplication because that's what really makes the topic interesting. So how do you add 2 points on the plane? So for today, in the remaining minutes, I'll just tell you how the addition works. So it is kind of like, if you had to take a guess, I think it's probably the guess that most of you would take. So the idea is that if you have a point, a complex number, which again, I'm thinking about it as a point. Okay, let's call this, if you have one point on the plane, which again, now we're thinking of as a complex number, and you have another point on the plane, which I'm going to call Z2. The way the sum is defined is that algebraically, it is like the entry by entry, coordinate by coordinate sum. So to add these 2 points, what I'll do is add the x coordinates and add the y coordinates. Okay, so the sum is going to be so the sum is done entry-wise. Okay. So the sum is done entry-wise. So you add the corresponding entries, corresponding coordinates. So for example, like just to do something like numerically, like just to do something quick here, and I'll kind of tell you. So like say if this had been the point, I don't know, like this could be if Z1 had been 3, 1, and Z2 had been the point, I don't know, let's say 1, 4, for whatever reasons. If I wanted to add Z1 with Z2, so I add the first entries together, 1 plus 3. 1 plus 3 gives me 4. So let's just write it, 1 plus 3. And then I add the second entries together, which gives me 4 and 1. So that would be what the sum corresponds to. Is that okay so far so good? Now, the cool thing is that, okay, like, again, like algebraically is not too surprising, maybe why you would do that. The nice thing is that this does have like a nice geometric interpretation, which is called the parallelogram law. So let me kind of write that down. So there is a way to think about this like visually, like, so there's like a geometric interpretation of the interpretation of this rule, which is called the parallelogram law. It says the following. So if you had, say, if you had this point Z1 and this other point Z2, let me see if I can draw them a bit better. Okay, let's put this one here. Z1 and this point Z2. Okay, what you can do to think about the sum more geometrically, what you can do is draw an arrow that starts from the origin and terminates at a given point. That's called like a vector, by the way. So you would draw an arrow that goes from the origin to the point in question. You would draw another arrow that goes from the point, from the origin to the point in question. Our arrows always would start at the origin whenever I draw them. Okay. And then kind of like with these two arrows, you can kind of like clone them. So you kind of copy paste them in order to build the parallelogram. So just imagine like copy pasting this other side here and copy pasting the green side so that it matches. So, kind of like you clone it, copy paste, put it so that it starts where the other one ends. Clone it, put it where so that it starts where the other one ends. You see a parallelogram, and the sum corresponds to this diagonal that is here. So the sum geometrically is the diagonal of one of the diagonals of this parallelogram. Is one of the diagonals of the diagonals. Diagonals of the parallelogram. Okay. Which is the way, by the way, if you have seen this before, how forces act. So like if you had like an object here and you're applying a force in this direction and you're applying a force in this other direction, the net force is the blue vector, but then that force is like that, you know. The resultant force would be the blue one. In practice, you don't have to use this picture, but it's kind of nice to know that it's out there. Yes. Like it is a thing, it is a vector addition formula for linear algebra. Yes. Yeah. That's why I said that I was want to tell you a little bit about vectors, like now, because yes. It's not needed, you can just kind of like stick to this point perspective, but it's nice if you draw the arrows to see what's going on. Okay? Yes.
Like, so when we write it in terms of like coordinates, what exactly does it have to do with like a number, like?
Well, the thing is like here we're just being flexible in what you call a number. So again, what are that's why I was starting earlier to saying what are the main features? Why do you, well, like how do when you talk about a number, what are the main things that you want to do with a number? Add it, multiply it. Right. Once you know how to add multiply, you can kind of like know how to subtract and divide usually. So adding and multiplying. There are other things that you may want to do with a number, like take a square root of a number, like the exponential of a number, logarithm of a number. What I'm claiming is that the reason why I'm calling these numbers is that we're going to add them. I just told you how to add them. I'll focus next time on how to multiply them. But then you can even do other things, like taking the square root of a number of a point on the plane, or taking the exponential of a point on the plane. So you can do all the things that you usually would have done to a number, you can apply to points on the plane. And because you can do exactly the same operations, you just keep calling them numbers. But now are called complex numbers because they're not on the line, they're just like on the plane. So it's just because you're able to kind of like extend the usual operations of points of numbers on the line to numbers on the plane that you kind of keep calling them numbers. Otherwise, you would call them vectors. So for example, in 3 dimensions, like for those who are interested. So in 3 dimensions, you can add points in 3 dimensions just by adding their coordinates, but you cannot in general, like take the square root of a point in 3 dimensions. But this is kind of something that can be done in 2 dimensions, in complex numbers, in 2 dimensions on the plane. Actually, Hamilton had tried to find, if anyone has heard about quaternions, he tried to find a way to do the same for 3 dimensions, and he found that you cannot do it. The best you can do is then go to 4 dimensions, and there's where the quaternions come from, and that's where the IJK comes from, from physics, because those are the symbols he used for the quaternions. But kind of the idea is if you are mathematicians are flexible in what you can use whatever word you want to use, but if you want to use a word that has been historically used, then you have to better check that it has many similar properties to to what that word usually was referred to as by, if that makes sense. Okay, just since we don't have that much time left, I'll kind of write the formula for multiplication. I'll work on it next time. So the multiplication formula is actually easier to express in terms of polar coordinates, and that's why also it is kind of measures well with polar. So the multiplication formula will be, is very cool. Well, before I give that, let's see, should I? Well, okay, I'll kind of I'll write this in more details next time, but okay. But now I will think about it with this arrow thing. So okay, so I'm going to tell you there's a way to multiply these two numbers, and these two complex numbers, or like another way of saying it is that there's a way to multiply these 2 points. Okay, so there's a way to multiply these 2 points. So I'll call that Z1 times Z2, because I want to think of it literally as a multiplication. Okay, so like that's why I'm using the same notation as a multiplication. Okay, so this is meant to be a new point. Okay, but here comes the trick. So the idea is that and I'll restart this next time, so like don't worry about it. But if you think about the points kind of like in terms of these arrows, right? This has a length, right? Or the distance to the origin, which is like this r from polar, right? So let's call this r1 because it refers to the first vector or the first arrow. This is usually called the magnitude or norm of a point. So there's like an r1, right? And then there's an R2 here, right? Like the distance of this point to the origin, R2. So the magic of the complex numbers is that you want the length of this new vector to be the product of the individual lengths. Okay, so and again, I'll kind of remind you this next time. I want the length to be the product of the individual lengths of the vectors, or like the arrows. But if you think about it in polar, what do you need? You need r and theta. So I have to give you what the theta should be. And the idea is that you add the angles of the individual vectors. That's kind of what makes everything work really nice. And you'll see why that happens next time. So what I'm saying is that you multiply the lengths and you add the angles. So if this was an angle theta1 and this is an angle theta2, the new angle will be theta1 plus theta2. Okay? So angles add, and lengths multiply. Angles add and lengths multiply. Oh, it is defined this way so that it works properly. Yeah. But at least I can kind of like show you something fun that does happen if you choose to define things in this way. You know, here's an example, and again, I'll repeat this next time because this is kind of like the most important example of what you're doing all of this so that it works this way. But imagine that you take, you know, imagine if you took the vector Z1 to just be the 0.01. Okay. And I want to do Z1 squared. Okay, you can multiply, you should be able to multiply a number with itself. So that's Z1 times Z1, right? What is the angle here? That's 90 degrees, right? So if you believe what I just said, that the angles add, 90 plus 90 is 180. So Z1 squared should have an angle of 180 degrees, right? So the angle should be 180, which is pi. So this is where C1 squared should be, right? But what should be the size of C1 squared? The size should be the product of the lengths, right? But this has length 1, right? Because it's like just a 0.01. So the length, this should have length equal to 1. Right? So this should be the point -1, 0, right? So if you think of this as being I, if for whatever reason I wanted to call this I, the red vector I, and I call the purple vector -1, that kind of makes sense because like the first coordinate is -1. I just found that I squared equals -1. And that is where like you introduce this famous like I thingy. So I'll kind of repeat that next time, but I just leaving you with something food for thought, like they like to say, you know? So you found something whose square equals -1, but like the squaring for this to kind of work, you have to use this rotation trick, this angle trick of adding them. And you'll see that this kind of like has like very nice properties. But again, like there's a lot of stuff going to happen. So let's finish here and I'll tell you a lot more like in detail about this multiplication. Because like recording.